This is the second part of a two-part presentation on the major named theorems in differential calculus. This video presentation will focus on theorems related to differentiability, the largest of which is the mean value theorem, but also Fermat's theorem for derivatives at extremes and Rolle's theorem. The mean value theorem is a theorem about the average rate of change. When we think about the word mean, we should think average. When we look at the conclusion of the mean value theorem, we should recognize that the quantity that we're looking for is a point, that's the number c. We're looking for a point, c, where the instantaneous rate of change given by the derivative matches the average rate of change, represented by the slope. In order to talk about an average rate of change, we must be talking about an interval. And so notice in the hypothesis, there is an interval. It's a closed interval from a to b, and I need to be continuous on a closed interval. In addition, I need to be differentiable everywhere between the points, and so the differentiability is required on an open interval. To illustrate how the mean value theorem is used, let's consider a function. Having identified our interval, we have endpoints at a and at b. And so I can talk about an average rate of change. The average rate of change of a function over an interval is the slope of the secant line. And so the slope of the secant line is given by the average rate of change. The conclusion of the mean value theorem is to claim that there is a point somewhere between a and b where the slope of the tangent line matches the slope of our secant line. So as I move along the curve, I'm looking for a point where the slope of the secant line and the slope of the tangent line match. And for the picture that I've drawn, here's a point where the tangent line is parallel to the secant line. This would be my point C that's guaranteed by the mean value theorem. The reason that continuity is required for this hypothesis is that if I allow a break in a function, I might not need to have a slope that matches the average rate of change. Here's an example of a graph. I've drawn a discontinuous function. I have an interval from a to b. If I were to draw my secant line from the endpoints, there are no points on the graph that have the slope that matches the average rate of change. I do not satisfy the hypothesis of continuity. My function must be continuous in order to guarantee it. On the other hand, I could have a discontinuous function that does have a slope that matches. Here's another discontinuous function. If I drew the secant line, I do have points. In fact, this one has 2 points. One is up at the top, one is down at the bottom, where the slope of the secant line and the slope of the tangent lines are parallel. But these points are not guaranteed by the mean value theorem, they just happen to exist. The hypothesis of a theorem are simply conditions that would guarantee it. They're not necessarily the only conditions that make it happen. Let's now focus on the second part of the hypothesis. A function has to be differentiable. Now, one way to be non-differentiable is to be discontinuous. We've already taken care of that. So the only thing that we really need to add is what happens if I'm continuous but not smooth. Here's a graph of a function that's continuous but non-differentiable because of the point where the function has a corner. The slope is undefined at that point. If I now look at my secant line to find my average rate of change, I get this slope. But because of the non-differentiability, there's no point where my slope of my curve actually matches the slope of my secant line. Notice that if I had tried to smooth out that corner, I would have gotten a point where my tangent line is parallel to my secant line. But because of having that non-differentiable point, I never get to guarantee the existence of that point. So how do we recognize when we want to use the mean value theorem? The mean value theorem has the potential of finding points where my derivative at a point matches the average rate of change. While the mean value theorem is probably the more important of all the differentiability theorems, there are two smaller theorems that we would like to look at. The first is Fermat's theorem. Fermat's theorem is a theorem that tells us what happens to the derivative at a local extreme. A local extreme is a spot where a function reaches a maximum, but it's not necessarily the overall maximum. Here's an example of a graph. My function has a local maximum at the point shown in red. This point is a local maximum because I can draw a small window around it so that inside this window it's actually the highest point of the graph. Notice that it's not overall the highest point on the graph because my graph continues to climb outside of my box. A local extreme is simply an extreme locally within a small window. The definition for a local extreme involves this value delta. Delta represents the size of my window. If my local extreme happens at a point C, then my window allows me to go up or down delta. And so between C minus delta and C plus delta, I am at a maximum or a minimum. Rolle's theorem tells us what happens to the derivative at a local extreme. So let's think about what happens if I am a local maximum. If I'm interested in the derivative at that point, I need to think about a second point, consider the secant line, and now imagine what happens as this second point moves towards the first point. In my picture, I've drawn Z to the left, my point Z to the left of C. For all of these points, because C has a maximum, my numerator is a negative number because f of Z is less than f of C. Similarly, Z is less than C, so I have a negative on the top. This means that my fraction is a positive number. On the other hand, if I think about Z being greater than C, my f of C is a maximum. So f of Z minus f of C is still a negative number, while the denominator is now a positive number, which means that my fraction is less than or equal to 0. The consequence of this is that if I think about the derivative from the left, it must be a positive number or a 0. And if I think about the derivative from the right, at the same point, it has to be a negative number or a 0. If I'm differentiable, then those two agree, and the only way they can agree is they're both equal to 0. If they don't agree, the derivative does not exist. As a consequence of this theorem, any points on a function where the derivative equals 0 or where the derivative doesn't exist receive a special name. They're called critical points. Now, not every critical point happens to be a local extreme, but if you're looking for a local extreme of a function, the only places they can occur are at critical points, where there's either a horizontal tangent or where the derivative doesn't exist. This function illustrates several different critical points. First, we look at where the function has slope 0. This function has two such critical points. The point to the right, where the slope is 0, happens to be a maximum. However, the second point, that's sort of interior, is a critical point, but it's not a maximum or a minimum. The next critical point is this point where the derivative is not defined. This point happens to be a minimum, a local minimum, because to the left and the right, the function is above that minimal point. Finally, we have this jump discontinuity. This critical point could be a maximum if the top point happened to be filled in. In the case that the top point is filled in, we happen to have a maximum at this critical point. On the other hand, if I were to fill in the lower point, then the function would no longer have an extreme value. The reason for this is if I were to think about a window, there are points to the left where the function goes higher, and there are points to the right where the function goes lower, and so it's not an extreme. On the other hand, the point on the top is an extreme because both to the left and to the right it would have been a maximum. Rolle's theorem is a function about derivatives as well. It's actually based on Fermat's theorem, but it can be thought of as a special case of the mean value theorem. Similar to the mean value theorem, Rolle's theorem is looking for a point, a number c, where the derivative equals some number, except this time the value of the number is not the average rate of change. The value that we're looking for is a spot where the derivative equals 0. We're looking for horizontal tangent points. The reason that Rolle's theorem is a special case of the mean value theorem is because it occurs on functions where on the interval the starting value and the ending values are the same. So let's look at a typical example. I've drawn a continuous and smooth function, so it's both continuous and differentiable, and we need to identify an interval where the left endpoint and the right endpoints have the same y values. So if I call this f of a, the value of my function at that point is right here. The only possible point that I would want to match to is this second point, and this would have to be my second point b. My function is continuous and it's differentiable on the interval from a to b, and my endpoints have the same height. To see this as a special case of the mean value theorem, if we think about the secant line connecting those points, the slope of this line is 0. Rolle's theorem guarantees that there's some point between a and b with a horizontal tangent. For my graph, I see that the point would have to have been at this point. The hypotheses of continuous and differentiable are identical to those that are required for the extreme value theorem. The reason I say that Rolle's theorem is about turning points is that if I think about a function and consider all the places it crosses the x-axis, Rolle's theorem guarantees that if a function crosses the x-axis at two different points and is differentiable between them and is continuous everywhere, there must have been a turning point between those points where the slope was horizontal. And so, for example, if I have a function that's continuous and differentiable, you'll always find critical points between the roots of the function. To finish this presentation, I'd like to end by showing the connections between the different theorems. Rolle's theorem has a hypothesis that my function must be continuous and differentiable. But the idea that f is continuous on a closed interval is exactly the hypothesis required by the extreme value theorem. And so the extreme value theorem guarantees the existence of maxima and minima for our function. But the other hypothesis of Rolle's theorem is that my function has the same value at the extremes. And so this tells me that there is an extreme value somewhere in the interior. Because my function is assumed by Rolle's theorem to satisfy the requirement that it's differentiable on the interval from a to b, we know that f prime of c has to exist. And so Fermat's theorem about the derivative at extremes implies that our function has a derivative of 0. So the conclusion of Rolle's theorem is really a consequence of the extreme value theorem and Fermat's theorem about derivatives. In a similar way, the mean value theorem is actually simply a consequence. If I think about my original function, f of x, and I define a new function for my secant line, then I can make a new function that measures the difference This new function, d of x, satisfies the conditions for Rolle's theorem. That is, because f of x satisfies the hypothesis of the mean value theorem, that means f of x is both continuous and differentiable. Because the secant line is a simple line, and d of x is the difference, that guarantees for us that d of x, our difference, is continuous and differentiable. Furthermore, because the secant line crosses the function at a and b, this tells me that my value of my difference function is 0 at both endpoints, which means it's equal. This means that my d function satisfies all of the hypotheses for Rolle's theorem. This means my d function has a derivative of 0 for some value between a and b. And the cool thing is, because my function f can be written in terms of my secant line, which has a slope given by the average rate of change, and my difference function, this guarantees for me that the slope of my f function at c is the slope of my secant function plus slope of my difference, which is simply the average rate of change. And so Rolle's theorem gives us a tool that allows us to show that the mean value theorem is actually true.